I will
So
send.
let's wait others 5 or 7 minutes. So after the 7 minutes, we will start today's lecture. Ah, okay, thank you. You sent me.
I have sent it's a tutorial. Right. It's a C programming language. And Visual Studio. I open the binary editor.
What is it? I don't know. I think it's not C++. It's
No, I mean this. It's somehow on the thought. It's thought, but I open this by the binary editor.
you open a binary editor, yes?
Yes, yes.
Mm,
And my thought it look like this. This.
you open a binary editor, then
Mm-hmm.
the binary editor helps you to convert the necessary, convert from the one format to the another format, yes?
Yes, yes.
Okay, it's the results.
Mm-hmm.
The picture you sent me, it's the result, okay? What kind of format what kind of format you use? I mean, um, which format you use is acceptable. I mean, like from
I
which
thought
format to the which format you converted.
that, but it's like the own editor for Visual Studio. Like when I choose, like we need to open the new project. We have another like open with, and I choose in place of was first it's related sorting order first of all. It's we see, but in have another direction redactor. I don't know how it's format. Maybe hexadecimal or просто hexadecimal number. Some of them. Mm, okay, the first photo it's which format it was. And second I choose.
You use and the first is so the picture you sent is two pictures. The first
Mm-hmm,
is the format you're converting from. Yes.
mm-hmm,
The
mm-hmm.
second picture is the format you converted to.
Yes.
Okay. Okay. I got it. I got it. And let me see your code.
Mm-hmm.
So what you want is what's your purpose here?
I just wanted to like how the temperature sees the dot, and I wanted to know by the visual, not by the like the temperature you will see it by now. By I just wanted how it will look like.
Mm,
I think it's a this thing what it I do, what I did. Like
mhm.
I think it's this.
It's ask value. It's
Yes,
decimal
yes.
data.
And the number is hexadecimal, right?
So it's kind of so you convert it from for example, you're given the decimal number, then you convert it into the three format: hexadecimal, ASCII, and I don't know others from the
No,
startup
it's
from.
a first like the row, first row, second row, third row, something like this. It's not it. It's like only the raw numbers.
Row number. Okay.
Yes.
Mhm. Good. Very good.
Mhm. Thank you.
Uh, so what kind of language is it's C
C.
or
C. C is.
okay? And you use Scribble, yes?
Mhm.
It's a Microsoft Visual C++. Or
Mhm.
you know, what kind of program is
Visual Studio.
Visual Studio? Okay.
Yes. It have a own bunny editor.
Mm, good. Very good. I highly appreciate this. So keep going, and you if you're going go practice and practice again. So in this case, like programming language, learning the programming language is kind of, uh, for example, you learn very um, perfect. Let's say very perfect. You know perfectly the C++, yes.
Yes. Yes.
Then you can easily learn the Java.
Yes.
Then you can easily learn other programming language like Python, PHP. Okay, but
Yes.
what I want to say is, to be honest, to be
Mhm.
very honest, is because I just know that
Mhm.
um, the program. Okay, it's very good. You started the program you write now as very one of the easy tasks, but we
Yes.
have very big project. I have seen very big project which other students did also. I also participated a big project. In big project, you not only use like a one page or two page, so you have to consider many components, and you write a lot of code there.
Yeah, and anyway, one time I did one big project in the dam. I mean, in the Unity. It was have maybe 13 step by the 100 row each one.
Yeah, like when you write the code, like
Mm.
then maybe because of the many code, because of the many code in the system, you will confuse. You know,
Mm.
you will
Mm.
confuse the meaning, you will confuse the concept.
Yeah.
Therefore, like one project is given to the many, like according, okay, in order to finish the one project, for example, if it's a big
Mm-hmm.
project, let's say real life project, um, normally the more than 20, or let's say mostly 20 programmer, software engineer will attend it, because some part backend or front end part will take the 10 software engineer. Other part, for example, front, let's say backend, and we have front end, yes, will take another software engineer. So according to this, software engineer works and works, and then one day they will finish this project.
Yes. So the first time when I just learned C and CPP in the church, it was really hard to me. But next, I'm starting to learn C sharp, and almost I learned the basic function syntax in the one unit C sharp. One week I'm learning, and the next week I'm already can taught this language. Now
Mm,
the this year I'm learning the Python. After C and C++, Python is so easy language. So on that
mm,
side of this.
like a Python, the difference between the Python and
Yes,
Java, like a
yes,
Python, you write a little bit less code
yes,
rather than a Java, because it's considered like a Python, because it's um, developed recently. Therefore, uh, it has some comfortability when we compare with the Java programming language.
Yes.
So, mm, anything else you want to say?
Yes, right. But something changed. Windows, it's anyways C++. It's a better idea. So when I found the one that, and he wanted to do one part, and the part was like in the Python was for more than 100 line, but in CPP it was less, maybe 13 lines, something like this. And I just like the C++, it's supporting with Windows or something like this better for this. Anyway, I like the CPP.
Mm, I'm also like using the C++ because uh, when you use C, in C, you have to write the many cards, and they have like uh, let's take for example C out and printf.
Yes,
In C++, we use C out. In
yes,
C, we use printf, and then in order to like display the, for example, integer value. So here you have to uh, write the, for example, uh, the symbol percent, and you have to write the D. Yes, if it's character, then you have symbol percent, and you have to write the C. Yes, like this in print. C out, it doesn't matter. In C out, in C++, sorry, it doesn't matter what kind
yes,
of type data type you want to display to the screen, so it doesn't matter.
yes, yes, that's it. And C sharp, it's after the C and C++ learning C sharp, it always something easier because to write in C sharp, it's a tonsor write line, like tonsor and write easy. Then the printf, it's easy too, but it's a ordinary word like the write or write line. I
Mm,
mean,
yes, yes. Okay. So let's wait 5 minutes.
okay.
Okay. Okay, let's start today's lecture.
Okay.
Uh, Today we will learn new topic. I think it will be interesting and more interactive for you. And today's lecture, you will gain uh, okay, a lot of information and a lot of new knowledge about the uh, computer architecture. So input output, we will talk mostly about the input output and its organization. And this topic is considered one of the important topic in computer architecture course. So our plan for today is we will talk uh, basic concept, and therefore I have to introduce you what's the input output and the concept of input output. Then we will again talk input output, the where we can use and the benefits. Okay, and we will talk its organization. So let's start. So basic feature of computer is its ability to exchange the data to other devices. Yes, so it means that you can exchange the data. You can use it's one of the important feature is in computer it data exchange. Yes,
Mhm.
when you want to exchange the data, what kind of devices you use? For example, you use flash card, you use disk, you use uh, other exchange the devices that you can exchange the data. Yes.
Mhm.
So why we use these devices? Because we need the communication, if possible. Yes. For example, uh, communication. I'm talking about the communication, which means that, for example, uh, you want to send your own data to the other computer, let's say, or you want to share your data, share your information with your friends or with your course mates. Yes. So in this case, you use flashcard disk or any communication devices. You plug into the computer and you load your information, necessary information, and you can give to your friends or the person you want to give. So it's one of the type of the communication, yes.
Mhm.
And application, uh, I mean, therefore, the devices, input output devices is necessary. And then application like integral part of home appliance, manufacturing equipment, transportation system, banking, and point of sale terminals. Uh, so what what does mean point of sale terminals? What kind of terminals you imagine when we say point of sale?
So, mm, no idea.
So you see the picture, yes?
Yes.
This kind of terminals is called point of sale terminals.
Oh, that's right.
Like,
From which we can pay for the something, right?
yes, yes, right, exactly.
So it means ATM machine also it comes inside, right? ATM machine also we can add.
Mm,
Sorry,
ATM machine.
ATM machine, yes,
Yeah,
also.
the same thing.
Hmm. So input from a sensor switch, digital camera, microphone, and or fire alarm. Uh, it's also important component of computer. Yes, an output like sound signal sent to speaker or digital signal which change the speed of motor. Open valve opens the valve or robot to move in specified manner. So it's a considered output data,
Mm.
output devices. Okay,
mhm.
when you send sound signal to speaker or a digital signal that changes the speed of motor. And also, computers should have the ability to exchange the digital and analog information with the wide range of devices in many different environments. Okay,
Mhm.
uh, let's go on. So, in addition to the processor and set of memory models, the third key element of computer system is set of input-output models. Yes, each model interface to the system bus or central switch and controls one or more peripheral devices. And input-output model is not simply a set of mechanical connectors that wire a device into the system bus. The rather input-output model contains the logic for performing communication function between the peripheral and the bus. As you can see in the picture, we have input-output and we have system bus and CPU. Yes,
Mhm.
in this case, we interfere. Interfere means we can influence input-output devices uh, i- with the system bus and with the CPU. The reason why peripherals doesn't connect directly to the system bus are as follows. Like this for one, two, three, and four. This is for reason as why peripheral doesn't connect directly to the system bus. What does mean peripherals?
Peripherals.
Let's let's translate this word
Mm.
into your own words. You can use translator.
It's like a device outside the device. It's outside that. Yes.
Yes.
Yeah, outside device.
Okay. Yes. Exactly. Uh, the data, um, the raw wide variety of peripherals. So it means that the reason why out devices doesn't connect directly to the system bus. So it means that the out devices, which is not directly connect to the system bus, we will learn the reason. Okay. The raw wide variety of peripherals. So a lot of different types of peripherals with different methods of operation. It will be impractical to incorporate the necessary logic within the processor to control the right range of devices. So it's impossible, which means that it's impossible to incorporate. Incorporate means like a combine the necessary logic within the processor in order to control the range of devices. So in order to control the many devices and connecting the necessary logic and combining the necessary logic to this is impossible. It's one of the reasons. The
Mm.
second reason is data transfer rate of peripherals is often much slower than that of the memory or processor. Therefore, it's impractical to use high-speed system bus to communicate directly with the peripheral. Okay, and
Mhm.
on the other hand, the data transfer rate of some peripherals is faster than that of the memory or processor. Again, the mismatch would lead to inefficiencies if not managed properly. Mismatch. What does mean mismatch? It doesn't match it means that doesn't match. Yes.
Mm-hmm. Doesn't simulate.
So speed should be the same, right?
Of course, yes. Yes. So the third reason is the data transfer rate of some peripherals is faster than faster than memory or processor. Therefore, it's considered as third reason, and it doesn't match to inefficiency if not managed properly. So if it's not managed properly, it will doesn't it is that like it doesn't match uh, to inefficiency. Okay.
Right.
Mm, Then peripherals often use different data formats and word lengths than computer to which they are attached. So we have different data formats in peripherals, like different data formats used by peripherals and word lengths than the computer to which they are attached. It's considered the first reason. So do you understand this?
Yes.
Okay, then let's talk about
Yeah.
input-output model. Has two major functions. So interface to the processor and the memory throughout the system bus or central switch. That's first function. The second function is interface to one or more peripheral devices by tailored data links. So here we have address line, data line, and control line, yes, which is connected in system bus. Sorry, which contains in system bus, yes.
Mm-hmm.
And we have input-output model, yes. The control lines, data lines, address lines are three of them connected to the input-output model, yes.
Mm-hmm.
So here we have links to the peripheral devices. Also, it's linked to the other peripheral devices. Yes.
Mm-hmm.
Okay. Then we have external devices. Input-output operations are accomplished through a wide assortment of external devices, which provide means of exchanging data between external environment and the computer. So external device attached to the computer by link to input-output model. So external devices attached means connected. So it's connected to the computer throughout with the helping of input-output model.
Mm-hmm. Sorry.
Then we have link. Yes, the link is a kind of type of method or type of kind of thing that connects the one system to the another. So we say link. So imagine that it has it used for connecting the something else. For example, it connects the one side to the another side. Yes.
Mhm.
So the link is used to exchange the control, status, and data between the input-output model and external devices. Yes. So external device connected to input-output model is often referred to as peripheral devices or simple peripheral. Now you know the full concept of peripheral devices. So what does mean? What does mean peripheral devices? So external devices which connected to the input-output model. In this case, we say peripheral devices.
Mhm.
Which devices is external device connected to the input output model. Then we say we can broadly classify external devices into three categories. Yes. First is human readable. Second is machine readable. Third is communication. So when we say about the human readable, yes, it's suitable for communication with the computer system. When we say about the machine readable, it's suitable for communication with the equipment. So when we communicate with the equipment, it's machine readable, yes. And when we say communicating with the computer user, it's human readable. And then when we say about the communication with remote devices, it's communication. Yes.
Mhm.
Okay. One minute. Please pay attention to this picture, this
Mhm.
diagram. So in this diagram, you can understand the general terms, the nature of external devices. So we have two components, control logic and buffer. And with the buffer, we have transducer, sorry. Yes. Control signals from input-output model comes to the control logic. And from the control logic, it goes into the outside, yes,
Mhm.
which is starts to input-output model. And we have data bits to and from input-output model. And we have data device, sorry, data, sorry, 1 minute. Data to and from environment. So data comes from environment and data sends to the environment. Data
Mhm.
comes to the transducer, data sends to the environment. Like this, also we have uh, this kind of environment. So control logic and buffer connected. Sorry, here
Mhm.
the data comes from control signals. No, sorry. Control signals comes from input-output model to the control logic.
Mhm.
Then see, control logic send its own data to the buffer, and also control logic send its data to the input-output again.
Stats maybe, yeah. Stats signal like that.
Sorry, yes, start signal. Then data, yeah, we have transducer, yes, and
Mhm.
data bits to and from input-output model. So buffer, the data can be come from the output model, and buffer data can be exchanged with the input-output model and buffer. I mean, data can be sent or
No, it's like driven by the Zoom.
so okay, so data can be sent or to buffer or to the
Mhm.
input-output model in this case. Okay, so
Mhm.
do you understand this?
Yes.
So the interface to the input-output model is in the form of control data and such signal. So we have two type of interface, yes,
Mhm.
control signal and control logic. So control signals determine the function that the device will perform, such as send data to the input-output model, accept data from input-output model, report status, or perform some control function particular to the devices. Data are in the form of set of bits to be sent to or received from the input-output model. Such signals indicate the state of the device. For example, read, not to read, to show whether the device is ready for data transfer. Yes. And we
Mhm.
have control logic associated with the device controls the device operation in response to direction from the input-output model. The transducer converts data from electrical to other form of energy during the output and from the other forms to electrical during the input. typically the buffer is associated with the transducer to temporarily hold the data being transferred between the input-output model and the external environment. Buffer size of 8 to 16 bits is common. Then we have keyboard and monitor. Yes, the best unit of exchange is the character. The card associated with each character is typically 7 or 8 bits in length. The most commonly used text card is International Reference Alphabet. Yes, and each character in this card is represented by unique 7-bit binary code. Characters are of two types, printable and control. Yes. So let's talk about the describe. Do you understand the concept of keyboard and monitor?
Yes.
Okay.
Yes.
Where is Rustamov?
I'm here.
Now you are Mr. Farov, yes?
Yeah, really? I just connected with my computer and it was so slow.
What happened
And
was
after I joined with my phone.
Okay.
Sorry.
Okay. So in your form, so your name is Farov and your surname is Rustamov, yes?
Yes, yes.
Nice to meet you.
Nice to meet you.
Okay, because normally I first time I see this name, Rustamov Farov. You are
No,
in my
Mr. Farov,
class.
you saw.
I saw.
No, you saw me before as Mr. Farooq. But Rustam, you maybe first time.
Okay. Okay, please try to attend always. Okay, let's talk about this drive. This drive contains electronics for exchanging data. Yes, control and such signals with the input-output model, plus the electronics for controlling the disk read and write mechanism. Yes. In fixed heat disk, we have like a fixed the disk can be fixed. In fixed disk, the transducer is capable of converting between the magnetic pattern on the moving disk surface and bits in device's buffer. So moving heat disk must also be able to cause the disk arm to move radially in and out across the disk surface. Okay. So let's talk about models. Models, input-output models. The major function, or requirement for input-output model fall into the following categories. So we have 1, 2, 3, 4, 5 model we have. We have control and timing. We have processor communication. We have device communication, data buffering, error detection. Yes. So during any period of time, the processor may communicate with the one or more external devices in unpredictable patterns. Yes, depending on the program's need for input and output. The internal resources, such as main memory and the system bus, must be shared among the number of activities, including data input output. So therefore, the input output function includes the control and timing requirements to coordinate the flow of traffic between the internal resource and external devices. For example, let's talk about for example, control of transfer of data from external devices to the processor may involve the following sequence of steps. The processor interrogates the input-output model to check the status of the attached device. Second is the input-output model returns the device status. And if the device is operational and ready to transmit, the processor requests the transfer of data by means of command to the input-output model. The first one, input-output model, obtains unit of data, 8 or 16 bits from external devices. And the 5 data are transferred from input-output model to the processor. Yes. If the system employs the bus, then each of the interaction between processor and the input-output model involves one or more bus arbitration. The preceding simplified scenario also illustrates that input-output model must communicate with the processor and with external devices. So let me show you the one video about input-output devices in order to understand the concept fully.
Mhm.
Let's wait this short video and try to understand the concept deeply, okay?
In this video, we're going to explain 4 strategies to address what we call input-output architectures. Now, the underlying question with all these 4 strategies we're going to study evolves around a single question. How much work is done by the CPU in an input-output operation? So the situation we have is that a system has a CPU which is in charge of executing as fast as possible machine instructions, but at the same time we have these input-output devices that need to perform certain operations. Now let's start with the first strategy, very simple one. It's called polling. Let's call it number 1, and it's very simple to explain because basically the premise is that the CPU takes care of everything. First, it has to ask devices if operation is pending, initiates the processing, and does also the transmission of data. So this strategy is very easy to understand. It's just the one in which most of the CPU, if not all, most of the work is done by the CPU. Now this is highly inefficient because if we have a system with a lot of devices, asking the devices if an operation is pending requires the CPU to spend a lot of time, and if the number of devices is very large, this could even turn into a very inefficient system in which most of the time of the CPU is wasted on asking devices if an operation is pending. The second strategy focus on reverting or reversing this step over here, and it's called interruptions. Now in the case of interruptions, which we call it number 2, the idea is that even though the CPU has to be executing continuously machine instructions, whenever a device, an input-output device, requires attention, instead of having the CPU asking for that, the device is going to notify the CPU, and the CPU is going to temporarily stop the execution of instructions and perform what is called an interruption service routine. So this is as if the CPU is still doing most of the work, except the step of asking if the device is ready to do some operation, some input-output operation. The device is the one notifying. Now the first step that occurs here is that the interruption is detected. In other words, the CPU detects that there is one device that requires its attention immediately. Now the fact that the CPU is going to stop doing what it's doing right now and start executing this interruption service routine requires first to save the context of execution. This is because the CPU temporarily is going to use all of its internal resources like registers, internal flags, things like that, are going now to be used by this interruption service routine. Therefore, we need to store a copy in memory of this context, so that then we can restore the situation when we are done executing the interruption service routine, and the CPU can proceed executing the program normally. Now the next step is one of the most important one. There is a table which is checked. This table is called the interruption vector table, and this table is used to perform a lookup operation in which we use the number of interruption that was received by the CPU. This table with the lookup identifies one slot, and this slot, all of them, contain the address in memory in which is stored the interruption service routine. So the idea is that there is a location, which is also in memory, by the way, of this interruption vector table, IVT, and this table has in each one of its slots the address of the ISR, or interruption service routine, that will take care of the operations required by every input-output device hooked to the system. After this interruption service routine has been executed, then we have to return to the way the CPU was working before, which means first we have to restore the previously saved context. In other words, we leave the CPU exactly as we found it in this place over here, as if this interaction service routine has not been executed. In other words, it's not going to leave any trace on the context of execution, and then the microprocessor returns to the regular execution. Now the key observation here is that we have changed this step about asking devices if they have an operation pending. However, the CPU still manipulates data and performs the transmission of data. So even though from this point of view the CPU reduced its work, it's still carrying quite a lot of operations as part of this input-output processing. Let's now look at a more advanced strategy, which is called DMA, which stands for Direct Memory Access. This would be our strategy number 3. Now, direct memory access comes from the realization that some of the input-output is done in blocks. Let's take, for example, the disk. Sometimes these blocks are 4 kilobytes. So rather than having devices connected to the system, CPU, memory, connected to the bus, and we have here a device, rather than having 1 or 2 characters that is produced by the device, or the input-output operations are based on characters, these operations are based on blocks, large blocks, 4 kilobytes. Now if we go back to the interruption service, what it means is that every time there is a new data produced by the device, the CPU needs to take care of all of that data and transfer it to memory. In other words, in this transmission, it's still requiring a lot of time for the CPU when we use, or when we deal with, blocks of information produced by these devices. The solution adopted by designers is this strategy called DMA, by which a new circuit appears here. This circuit is called DMA. Now the DMA is precisely hooked to the bus, or connected to the system, to remove the responsibility of the CPU by making this transmission. So the CPU now, what it has to do is program the DMA operation. So it tells the circuit 3 things. It tells the circuit which device needs to be served, which device requires the transmission of a block. It tells also the number of bytes of the block, and finally a memory location for the transmission of information, either from the device to the memory or from memory to the device. So now the CPU, the only thing it does is it provides these 3 parameters, and the DMA from then on takes care of supervising all the transmission of data between the device and memory, and the CPU can keep executing the regular instruction. So as we can see, the main difference between strategy number 3 and strategy number 2 is that one significant portion of the handling of the data, especially in the case of block-based devices, such as, for example, hard drives, is now passed on to this more sophisticated circuit called DMA, and the only thing that is needed from the CPU is some basic programming of this circuit, and the rest is being taken care of. Once a device finishes this transmission, still the CPU needs to be interrupted. In other words, we're still relying on the interruption-based mechanism, such that the CPU then checks for errors, and in sometimes it programs the next operation. So this is a scheme that is fairly efficient because by brief connections of the CPU to the DMA, we are capable of programming the transfer of a fairly large number of blocks between the device and memory. So this is strategy number 3. And the next step is to evolve even further on the type of computation that occurs without the intervention of the CPU, and this strategy is called channel input output. This would be strategy number 4, and it's based on one circuit which is much more sophisticated than the DMA, which is called the IOP, or input output processor. Now this circuit is still connected to the regular system as we know it, with the CPU, the memory here. But now the difference is, rather than having the devices directly connected to the bus, what we have is one or several IOPs, and each one of them takes care of all the operations for more than one device. Actually, these microprocessors are capable of dealing with more than one input-output device. So as you can imagine, this type of a structure or architecture is more suitable for sophisticated systems that have large numbers of input-output devices. Now the difference with previous strategy is that the CPU now again programs the IOPs, but this programming that occurs here is different from the programming of the DMA because the CPU is capable, or rather the IOP is capable of executing high-level input-output operations. For example, suppose we have to transfer a file which is in memory to disk, and this file has a large number of sectors or blocks. In the DMA approach, the CPU would have to intervene every time a blocks need to be transferred. IOPs, on the other hand, are capable of understanding higher level input-output operations. Therefore, the CPU would only program the IOP to say this file that you have in memory needs to be stored in disk, and that's it, and then check again that the operation has been done successfully. So as we can see, these 4 strategies for input-output vary significantly on the amount of work that is performed by the CPU, to the point that we can represent into these 2 graphs over here. Suppose here we plot the CPU time that is devoted to input-output. We would be able to plot the 4 strategies we have described, or the 4 architectures, as follows. Polling would be at the top because it's the one that requires more CPU time. Interruption would be slightly lower because the CPU doesn't have to go and ask devices if they are ready. DMA would reduce the amount of time that CPU dedicates to input-output because it takes away all the complexity of transferring blocks between the device and memory. And finally, channel input-output would be the lowest one in CPU time devoted to input-output because these microprocessors are capable of executing fairly sophisticated or high-level input-output operations. But at the same time, we can draw this other graph in which we can plot the circuit complexity. And the circuit complexity, as we can see, starts with a very low value for polling because the circuit that is needed is barely nothing. The CPU is asking the device if it needs an operation, it's taking care of everything. Interruption is a bit more complicated because the notion of an interruption controller appears. We need this lookup table, we need the service routines stored in memory. Option number 3, DMA, is more complex because now we have a specific circuit which is capable of executing some basic operation, mainly a loop, but is still fairly much more complicated, and therefore the number of transistors or gates required to implement the circuit is much larger. And of course, up here would be the channel input-output because these IOPs we have here are much more complex circuits than the DMA and require therefore a large number of gates.
Okay, do you understand the concept of the video?
Yep.
Okay, let's continue our lecture. Good. Okay. So processor communication involves the following. We talk about command decoding, and we will talk about data. So the input-output model, accept commands from the processor and send as a signal on the control bus. For example, input-output model for a disk drive might accept the following commands: read sector, write the sector, seek track number, and scan the record ID. The later two commands each include the parameter that is sent on the data bus. Yes. So when we say about the command decoding, so input-output model accept the commands like an input-output model receive commands from the processor and send the as a signal on the control bus. So data are exchanged between the processor and input-output model over the data bus. Yes. So over the data bus, data can be exchanged between the processor and input-output model. Then we have stats reporting, address recognition. What does mean recognition?
Recognition is saving or something.
Now, recognition means the address recognition means recognize, you know something or introducing something else. Okay. Stats reporting. So let me explain stats reporting. Because peripherals are so slow, it's important to know the stats of the input-output model. So you have to know the importance. You have to know stats of the input-output model because peripheral is slow. Yes. For example, input-output model is asked to send the data to the processor. It might not be ready to do so because it's still working on the previous command. This fact can be reported with the such signal. Common such signals are busy and ready. There may also be signals to report various error conditions. When it comes to address recognition, just as each word of memory has address, so does each input-output device. Therefore, input-output model must recognize one unique address for each peripheral it controls. On the other side, the input-output model must able to perform device communication. This communication involves commands, such information, and data. Let's talk about data buffering. Essential task of input-output model is data buffering, yes, where the transfer rate into the and out of main memory or the processor is quite high. The rate is orders of magnitude lower for many peripheral devices and covers wide range. Data coming from main memory and sent to input-output model in rapid bursts. What does mean rapid burst?
Bus. Rapid buses.
Yes.
So like maybe something happens faster.
Yes, something burns fastly.
Mm.
Something will exchange the fast. So we have and also error detection. Yes.
Mm.
Finally, input-output model is often responsible for error detection and for subsequently reporting errors to the processor. One class of errors includes mechanical and electrical malfunction reported by the devices. Yes.
Mm.
Another class consists of unintentional change to the bit pattern as it's transmitted from device to input-output model. Some form of error detecting code is often used to detect transmission errors. For example, ERA character code occupies 7 bits of byte.
Mhm.
8 bit is set so that the total number of first and the byte is even or odd. When byte is received, the input-output model checks the parity to determine whether error has occurred. Yes. Okay, this is the full organization, output model structure, block diagram of input-output model. Let's learn this. Let's what let me explain this one. We have data register, stats control register, stats or control registers. We have external device interface logic. We have input output logic, and we have external device interface logic. Yes. Data lines comes into data register and stats or control register, and data register sends some data to input output logic. Stats or control register also sends to the input output logic. So the data status control data can be sent to external devices, device interface logic. Stats also can be sent to this path, and control can be exerted from external device interface logic. Here we see the same thing: data, stats, and control. So see, input output logic interacts and communicate with the how many 4 parts: external device interface logic, data registers, stats and control registers, and so on. And we have address line and control lines. Yes.
Mhm.
So the programmed input output. So 3 techniques are possible for input output operation. Guys, can we make a break for 5 minutes?
Mhm.
Okay,
Okay.
let's
Okay.
have a break for
Okay.
5 minutes, and after the 5 minutes we will start again.
Okay.
Okay.
Thank you. Okay. So street technique. With programmed input output. So let's talk about with programmed input output. Data can be exchanged between the processor and input output model. The processor executes a program that gives a direct control of the input output operation, including sensing device sets, sending a read or write command, and transferring the data. When processor issues the command to the input-output model, it must it must wait until the input-output operation is complete. If the processor is faster than input-output model, this was wasteful processor time. With interrupt-driven input-output, the processor issues input-output command, continues to execute other instruction, and is interrupted by the input-output model when the latter has completed its work. With both programmed and interrupt input-output, the processor is responsible for extracting data from main memory for output and storing data in main memory for input. The alternative is known as direct memory access, DMA. In this mode, the input-output model and main memory exchange data directly without processor involvement. Okay, this table shows the relationship among these three techniques. In this section, we explore programmed input-output, interrupt input-output, and DMA are explored in the following two sections respectively. We have input-output to memory transfer through our processor, and we have direct input-output to memory transfer. Please note that we have no interrupts in programmed input-output when it comes to input-output to memory transfer. But use of interrupts, interrupt-derived input, we have an input-output to memory transfer through our processor. So what about the second part? Who wants to tell me?
Maybe like the transfer from that from one device to another, like that have something information in the memory and it does another. Wait. From from input
Yes.
device to output transfer.
Yes, yes. So like a direct input output to memory transfer, so we don't have any interrupts. Yes, but when we say about the use of interrupts, when it comes to direct input output to memory transfer, we have which type? We have direct memory access type. Okay. Let's move. Let's move to next page. Here we can talk about overview of programmed input output. Then, so this part you have to read by yourself, okay?
Yes.
I will skip this part. So let's talk about input output commands. So we have commands, yes, to execute input output related instruction. The processor issues address specifying the particular input output model and external device, and input output command. There are four types of input output command that input output model may receive when it's addressed by processor. Yes, control and test. When we say about control, use it to activate the peripheral and tell it what to do. For example, magnetic tap unit may be instructed to rewind or to move forward one record. These commands are tailored to the particular type of peripheral device. And we have tests. Use it to test various start conditions associated with input-output model and its peripheral. The processor will want to know that the peripheral of interest is powered on and available for use. It will also want to know if the most recent input-output operation is completed and if any errors occurred. So in this case, the task model is important. And we have read and write. So input-output model to obtain item of data from peripheral and place it in internal buffer. It's considered as a read. So when we say about read, yes, sorry, input-output model obtain, receive item of data from peripheral devices and place it in internal buffer. Place it in internal buffer, which means that it move the item of data from peripheral device, which is this component will place it in internal buffer. The processor can then obtain the data item by requesting the input-output model place it on the data bus. So let's talk about the write. So do you understand the concept of read, guys?
Yes, yes.
Yes.
Okay. So let's talk about the write. Cause the input-output model to take item of data from the data bus and subsequently transmit that data item to the peripheral. Yes?
Yeah, we understand it also. It's understandable.
Okay. 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 Here we see 3 techniques for input of block of data. I think it's enough for today because we already go out of the time. So guys, do you have any question regarding today's topic?
No. Okay.
No?
Okay. So please try to attend more actively, more attentively to other classes. Okay. And we will discuss more about the topics in computer architecture.
Okay.
Thank you.
Okay,
Have
thank
a
you.
nice day.
Thank you.
Have a nice day.
Have a
Have a
nice
nice
day.
day.
Bye.
Yeah, bye.